Hi, I'm Daniel Pyke. I'm from Sensonic. Thank you for joining me today this afternoon. I'm here today to talk to you about sensorless wayside sensing. That's not senseless wayside sensing, so I'm not going to waste your time. This is all about sensing things without actually adding sensors to the track. So, let's begin. So you've probably heard about data-driven railways or intelligent railways, intelligent rail, digital rail, whole host of terms. But it's all about, exploiting the ability that we now have to monitor pretty much everything, everywhere, all the time. Now that gives us access to a huge amount of information if we choose to use it and if we choose to install it. But that gives us a huge amount of data. Now that for some people is a dream, but for others is almost death by data, drowning in data. That's a real problem. One of the examples that I've got of that is simply that McLaren Formula One team, they have the ability to monitor hundreds and hundreds of channels of data on their cars, and they do. But during races, they only look at a few dozen. And that's because they're the important few dozen that they can change during the race and that affect their position and how likely they are to win. So looking at the right critical data is really important to success. So I mentioned, if we choose to install them. Why would I say that? Well, because implementing things on a railway is difficult. You've got big problems with access. We all have. We all know there's a problem with actually just installing them, physically getting to site to do it, but also maintaining them afterwards. How do you clean them, maintain them, repair them when things go wrong? And there's another challenge, obsolescence. How do we make sure things are there for the long term? Railways last a really long time. If we want to put something there, we want it to last a really long time. But how do we do that when technology upgrades continuously happen and replacement and obsolescence and support for older technologies? How does that work? And if we're not careful and we don't select things very carefully, we can end up putting so many things on track. We end up with something that's not maintainable because of all the wires, all the cabling, all the requirements that they are. You can end up with this mess that's not maintainable or makes the railway not maintainable. And that's when we need something we need to avoid. Now, obviously, this isn't a real example, but you can get my point that if you don't make selective choices about what you put on track, you may end up with something that hobbles you later down the line. Now, I hear people in the background saying, well, what about Wi-Fi? What about wireless? What about 3G? All that sort of stuff. Well, yeah, okay. Yeah, you get rid of some of the wires. So let's have a look at those a bit more in detail when we get to sensors that no longer need to be plugged in. So let's make all our sensors wireless instead. We've got that capability, but it also poses some real challenges as well. Yes, you avoid that massive trackside cables to power and return data back to base, and you avoid the challenges of putting tamper time through it all, or rats chewing through cables and all those sort of things that we know happen. But it also gives us some real challenges as well. First of all, the technology that supports that wireless, that's forever changing. In my time using mobile phones, we've gone from 2G right through to 5G. 3G is being switched off this year. 2G had a good innings, 42 years. It's going to last. 3G, 22 years, roughly half. 4G, would we guess at half again? Maybe 10 years. I don't know. But the challenge is we're putting things out there that we need to be able to support long term. That gives us a challenge, particularly when technology moves on so fast. We've also got the challenge of cybersecurity. Each of these individual sensors is then a way into the network, potentially, and potentially a target. That could be a target from Fred in his shed, who's a hobby hacker, through to state-sponsored terrorism, and all of which have happened to the railways, and all of which are, railways are a legitimate target for many. And so we have to make sure, or try to ensure, that everything is cyber secure. Putting communications over wireless just adds an extra layer of access for people that actually don't need to physically interfere anymore, making it far more difficult to trace them as well. And lastly, we're putting all these sensors, making our railways, wireless loud. What about how do we power them? How do we get the power that they need to generate them back to site? And typically that's batteries. Sometimes they might be augmented by solar, but it's batteries. And that generates a whole risk of us not being able to maintain them, batteries running flat, having to go out and replace these trackside, and that goes back to how maintainable the solution is in track. giving us extra maintenance work, and that's not really what we need. Now, batteries might last a year, 2 years, it really depends on the solution, but they are going to need to be replaced, and that also generates battery waste. The railway doesn't have a great history of picking up its leftovers from track. I'd hope batteries are going to be different, but I suspect it won't. And we'd have the challenge of, we create waste, we have to maintain it. We have to pick it up and deal with it responsibly. So power is a real problem putting things trackside, particularly for anything that's using power all the time. We have to be able to consistently give it power supply in order for it to work for us. But I guess, you might ask, well, okay, what's the other choice? We can't have sensors with wires, we can't have sensors without wires. Where does that leave me? Well, there is actually a choice. So, I can talk to you about fibre optics as a potential. And now don't look at me strangely all at once. Fibre optics are used widely across industry, and many different industries for that matter, because they're reliable, they're robust, they've got a good long lifetime. The first cables we pushed across the Atlantic are still functioning perfectly well, and they're relatively inexpensive, so it doesn't actually cost the earth to use those. And because of all those really useful characteristics, they make up the backbone of many, many safety critical systems throughout many, many different industries. That might be banking, our signalling systems, it might be communications, through to defence. All these systems use fibre optics as the backbone of communications because they're safe, in use, they're not going to hurt anyone if someone cuts the cable by accident. They're passive, you're shining light through a glass fibre. It's not an active part of, it doesn't carry particularly large amounts of energy, and it's got great electromagnetic compatibility. It's not going to interfere with signalling systems on the railway, for example, because you're shining light down a glass fibre. It doesn't generate EMC, and it's tamper resistant. You physically have to get to the infrastructure, the fibre optics, and then even then, if you've got access to it, it's really difficult to tamper with it in a way that can't be detected, because you have to unplug it to get plugged into it, and that's a real challenge. And that's why we use it for lots of safety critical systems, and why we've got decades and decades of railway experience using this, and in lots of other industries as well. So it's not an unfamiliar technology. It's present down most of our railways. Running down the side in these cable troughs will be obviously signalling cables, power cables, but probably also fibre optic cables for communications and signalling purposes. So it's not a technology we're not experienced with. But what we're not experienced with is the ability to use them for something more. So what else can we do with them? Well, there's actually a technology that's come along called fibre-optic sensing. That allows us to use the actual fibre-optic cable itself as the sensor. So whilst my presentation title was Sensorless, you'll hopefully allow me the leeway to use existing fibre-optic cables as our sensors. Now this video, I'll briefly show, explains how the technology works. Now hopefully most of you know how fibre-optic cables work. You shine light pulses into the fibre at one end, you get light pulses out at the other, and you can decode those to transfer data quickly over long distances. Now, not all that light makes it through the cable, and that's what our technology is based on. So let's have a look at how that works. So we shine light pulses down the cable. However, there are various different points in that cable called scatter sites where light is reflected back. A portion of the light is reflected back. Now that reflection is what we actually use to reveal information about what's happening along the cable. Vibrations of the fibre, they affect how that reflection comes back to us. And because we know the speed of light through the fibre, we can detect where along that it's happening. So we know the vibration distance, we know its frequency and its amplitude, and that allows us to extract information about what's happening along the length of that fibre, along the entire length of that fibre, in a way that then gives us information. Now that is effectively, you could think of it of slicing that cable up and turning it into thousands of mini microphones along its length, because they're each looking for vibration data, and that reveals information to us that we can then use to detect what's happening along the track. So what we're doing is using the reflections to essentially listen to our railway asset. And that's about, the technology is called Distributed Acoustic Sensing, because the vibration affects the reflections coming back along the fibre, and we analyse those changes to determine where it is along the fibre and the amplitude and frequency of those vibrations to give us information. Then we use some clever AI and machine learning to determine, well, actually, what's happening along those things, what events are happening along that cable. Yeah, I guess the real key advantages are you're using standard optical fibres. So one, it's an understood technology. Two, it's probably already there because there's lots of it out there. And so you're not requiring new sensors on track, and you're not requiring new sensors on trains. That's the other way of doing it. You've also got really, really long range of sensing ability. So one sensing unit can monitor 100 kilometres of fibre. So it's a controllable amount of equipment to roll out, and one sensor can start protecting 100 kilometres of route in a relatively short space of time. Now, how good is it? Well, it's sensitive enough to detect people walking nearby. It's in fact its most common use for distributed acoustic sensing is border protection, pipeline protection, security, to listen for people trying to interfere or cross borders, and that's where you'll see this technology used more extensively in other industries. But it gives you the ability, because you know that fibre is always there. You can listen to your network 24/7, or rather, some AI and computing power can listen to it to detect things where things are going right and where things might not be, to give you alerts in real time of what's happening on track. So what's it actually mean? You know, what can you use it for? Well, there's lots of different technology applications. I'll talk about 4 here that we commercially sell. So we've got security. You know, you can detect people walking, digging, and even stealing cables that are out in sight, because security is where this technology probably originated. You can also, because you can, looking at ground vibrations, you can detect things like landslides and rock falls, or mudslides, landslips, whatever you want to call them. But ground movements you can hear, because they generate vibrations. You can also detect very instantaneous events like a flashover. The big bang from a flashover fault might trip and may blow clear, but the damage is still done. And how do you actually find that fault? There's a recent RAIB report where people were wandering around track trying to find an electrification fault for 4 hours before a train nearly ran them over, a diesel train. They couldn't find the fault. Why did they have to wander around? Because they didn't know where it was, because they had no idea of which distance down the track. We can locate things down to around 10 metres of resolution, so you get a really good, quick to find fault or inspect. And of course, those of the more track related things, you can listen to your infrastructure. Almost from the sound of things when things are going right and when things are going wrong. Well, we do exactly the same with technology. We listen to the track and note changes and highlight those changes. And I'll give a brief explanation of each now. So, as I say, it's sensitive enough to hear people walk. Now you think, is it really? Well, yes, it is. I'm going to show you a little video here. This was actually set up in an installation that we've got in Austria. What you've got here, obviously trackside, you've got an inset with a Google map, and you've got what we call here the waterfall. I'm obscuring with my face, but what you've got here is effectively track distance across the x-axis, and you've got time down the y-axis. We call it a waterfall because data flows in at the top and gradually descends to the bottom. And we use colour to highlight where vibration is happening, or vibration intensity, if you like. So what I'll do is play the video now, and you'll see hopefully that the fact that you can detect where my little friend here starts coming walking past, you can detect each and every one of his footsteps as he walks down the track. Now that's okay, that's great, but what we actually have is AI looking at this and saying, well, hang on, oh, there's an alert there, there's someone walking down my track and there shouldn't be. So not only have you got an instantaneous alert, you also know exactly where it is on track. And this can function 24 hours a day, 7 days a week without intervention, highlighting only the bits where people need to look at. And of course you can integrate that into security systems and send out responses and all sorts of things like that. But the detection technique is simple. You listen for when you've got an intruder on track. So here's another example where this guy's walked a site. You can see he's walking down here. He's now opening the cable troughs, and maybe now he's going to think about stealing some cables. Well, obviously we're not going to really steal them, but as soon as he starts touching, interfering, moving these cables, you'll see they start lighting up like a Christmas tree, which generates alerts, which then can be triggered in real time to send them to security services, trigger more surveillance, trigger a police response. All these sorts of things that could happen live 24/7. So obviously those last videos were set up with help with our partners and clients to detect things in track and demonstrate the capabilities. Well, here's actually an installation where we were actually looking for something else, but we detected someone digging through the track. And we see them start to dig. So this is a waterfall. The green lines are actually trains going past. So this is actually real life data. So you can see, as I say, the x-axis is the distance, the y-axis is time, with newest at the top. So you can see this guy started digging. He then had he started digging, he had a little bit of a break between trains, then he started digging some more, and then he actually cut through the cable. He dug through the cable. Now, most systems, when they are broke, stop working entirely. Well, actually ours doesn't. It carries on, so we know exactly where the break is along this cable, because we still get data all the way up until that point. And we've had all this time to intervene if security resources were on hand to do so. So we get one, really precise information of where the problem is, which can be difficult, particularly in miles and miles of countryside. But equally, we have this response time where we have all this time that we could do something about it. And that's all we're doing, is we're an information system, an information provider, to allow the railways better insights and to actually respond in the best way. Equally, here's an example where we're detecting the sensitivity capabilities with the customer, where they actually allowed us to simulate rockfalls on their track. And here, we've got waterfall. We're obviously very zoomed in, so it's quite pixelated now. Similar sort of thing, waterfall, and we've got a track environment, and usually we were permitted to drop rocks in it. So here we can see rock starts falling down the hillside, and obviously you see here the ground vibrations, and we get an alert detected to say that, well, actually there's a problem here. An alert goes to the operations team. They look at it, decide what they're going to do, to give information about what's happening in real time, and gives the ability for people to stop incidents turning into accidents. Now obviously that's a simulation to determine how good our detection systems were, and I'm pleased to say that they're so happy they actually started rolling it out to real life environments. And here you can see some of the examples we did with trials of them. Here's actually a very small sort of rock slide that's come down onto the track. Here you can see something that, well, I wouldn't want to run into, size of probably a small wheelbarrow or something like that. And there's an equally small one here beside me, behind my head actually, which shows the the capabilities of our equipment, because we have alarms generated automatically for each one of these events. And equally, one of the others, far more picturesque picture, where we've got an actual real substantial rock slide onto the track, which obviously required cleanup. And we have stopped trains via the alerts we've been sending to stop accidents happening, and that's a real success for the system. Yeah, quite proud of that, to be fair. Another application is catenary flashovers. These are hopefully one-off energetic events that cause either the fault to blow free or a protection system to cut in to cut the power. Now the problem is actually, how do you find that fault? The protection system might cut power to a kilometre, maybe more, maybe many kilometres of track all at once. So how do you actually find that fault? Well, one of the ways is actually listening for the bang. Now I'm going to play a little video. It's a little loud. I'll give you a warning in advance. So headphone users, just shelter your ears now. So this is a trial that we did with one of our clients that showed we could effectively pick up this vibration, because it makes a really loud bang, and tell them exactly where it is. And why is that important? Well, because these things happen in the middle of typically in the middle of nowhere, in the middle of the dark, in the middle of the night. How do you find them? You're looking for a sooty skid mark that might not even be there anymore. Sometimes you've got a tree dangling over, and yes, you find it and it's obvious, but sometimes it's not. Yet the damage is still caused by the flashover. All those sparks are metal that's been burnt away. and that's damage. Now that leads to unreliability potentially in future. So how do you find these things? Well, there's a recent report from the RAIB that I was reading that there was a couple of guys wandering around on track trying to find electrification fault for 4 hours before, and that was, they hadn't found the fault by that 4 hours. The reason the RAIB were investigating because they almost got run over because they scheduled a diesel train through there. Now, if we could, why were they spending 4 hours looking for a fault when we could tell them where it is in 4 minutes? One, safety improvement, but two, it's a real massive time improvement. And if you actually know to within 10 meters where the fault is, you've got a really good idea of being able to actually find the fault. Some of these faults are difficult to find. You're looking for small black skid marks of stuff that burnt pigeons or things like that that aren't there anymore, but they still cause the damage, and that leads to future potential reliability issues, catenary, and dewirements, which nobody wants. So this is a way of finding them fast. Simple. So a subject that's close to my heart, track condition monitoring, is another application. Humans are great at understanding changes in noise. If your car starts making a funny noise, it's usually expensive. And that's the same for the railway. If it's changes in noise, then that means something's changed, either the vehicle or the track. And because we're listening to every vehicle and the track all the time, we can detect changes in the infrastructure performance, and that gives us, we do that via what we call a sonic track index, which basically is a sonic fingerprint of how that infrastructure performs. Now, what changes that? Well, I'll briefly describe some of the things that we can see. So lots of things can affect track vibration, lots and lots of different things, and this is not an exhaustive list. This is a list of things we've seen in track and detected via vibration changes. So obviously broken sleepers, ties, however you want to call them, depends on which side of the Atlantic you're on. We can see surface defects, squats, wheel burns, even loose fish plate joints, loose insulated joints in this case, broken rails. At the top right there you can see is actually a dipped weld. It's a little difficult to see, but you've got a dipped weld that introduces extra vibration to the track, and obviously ballast degradation, which you can see because of it, and that we detect via the vibration change of the track. And missing fasteners, the list goes on. But these are some of the examples that we've taken from real life environments where we've deployed the technology. So I guess, what's that look like when you're looking at the data? Well, here's what it looks like on screen. If I briefly explain, you've got time on the vertical axis, same as previously in the waterfalls, and you've got distance across the bottom. That could be GPS coordinates, kilometers, miles, whatever units you prefer to work in, really. And what we can see here is the sonic track index. Now this is the change in vibration. So we're not looking at absolute vibration now, we're looking at changes. Because we know a crossing is always noisy. If it changes in noise though, that's when we're interested in. If we know a joint is always noisy, it's a change in the noise that we're interested in, because that reflects a change in the performance of the infrastructure. So here you can see at the centre we've got a change in vibration. We've got something that starts here, rapidly evolves and gets bigger and develops into a noisy bit of track that's about 25 meters long in this case. So what was it? Well, I can't tell you. I can't tell you from just this data, but I know there's something there, and there's something that we need to be interested in. And that's what we're about. We're about providing information. We can't give you all the answers, but we can give you much more information and insight. So, well, what happens? What actually was there? And the answer is this. This is what we saw when we visited the site. A very large, rather worrying crack under the head of a rail and starting to turn down. Now, as is typical with site inspection photos, the wrong rail's in focus. But anyway, I hope you get my point that this is a serious defect. The only reason that the infrastructure owner went to site, this is live track, the only reason they went to site, because we told them to. Because we said, that looks worrying, go and look at it. And that's so they did, found this, and obviously then needed to change that rail and re-level the track, because it was obviously a significant safety issue. But that's real defects that we're spotting in track, giving real information to railways to say, well, actually, we can help fill in the gaps between some of your measurement vehicles. We can help give you data that's access to data that's current. So how does that work in real life? Well, in real life, you've got a fibre optic cable and you simply loop it into a box. We only need one dark fibre in a cable, in a bundle, to transform that railway and enable its distributed acoustic sensing. We turn that into acoustic, we turn the fibre optic cable into an acoustic sensor, and we monitor and classify the vibrations from that. And that can be up to 100 kilometers of fibre, typically around 80 kilometers of track from each box. And that gives you the ability to, one, roll it out quite quickly, solve particular challenges. So whether it's an area that you want to monitor for landslides, or you've got a cable theft issue, or whatever that might be, it's something that you can roll out reasonably quickly. It's something that you can then maintain because you've got one box per 80 kilometers rather than a sensor every 5 meters. So it gives you the future maintainability of the network. And we're building on what we can detect all the time. We've got an active research environment to do just that. But the idea is we give you information about the track, key events, security, landslide, track condition, flashovers. We give you knowledge about what's happening on track in a simple and easy to roll out way. You don't need to go put sensors all over the track if you want to secure against any of these issues. We have a simpler, easier solution. So I've gone through 4 of the applications, some of the examples that we've got from real life track. Hopefully that's given you an idea of some of the capabilities of distributed acoustic sensing and some of the problems that fibre optic sensing might help you solve in some of your future projects. I think that it's an interesting technology. It's really useful in being manageable in future, and that's one thing that we need to constantly have at the back of our minds, is how do we build a network that not just works today but also works next month, next year, next decade, and let's hope next century. So thank you very much to PWI for having me. I'll leave my details on screen in a moment, and what I would like to say to every one of you who's joined the call today, thank you very much for listening. If anyone wants to get in touch, they can certainly grab my contact details here, or get them through the PWI, or find me on LinkedIn, whichever way works for you best. I'll go to the chat box now and hopefully be able to answer some of your questions.